In the olden days, picnics were larger.
Families were larger. But when the Black Death came through, it was something else. Exciting.
Okay, go ahead.
No, we're
Finding a spot for a picture.
right here.
All right. Oh, good. This one?
No. That rock there. See anything funny about it? Have you ever seen rock like that or something like that before? Like at the beach, where you get a tidal current washing over the sand? These are current ripples.
Oh.
So the water was actually flowing in this direction and washing the sand up and then depositing it in the front of the ripple.
Could you do that one more time with me down closer to you?
Sure.
So that it'll look good on the dome. All right.
Okay, is it pointed?
It just doesn't matter. It's
It's
everywhere.
pointed well enough.
It's everywhere.
Okay, these are current ripples right here. They were formed when this was a beach sand, and the tidal currents were washing over this and forming the sand into ripples exactly the same as you would see at the beach today. Now the rock itself is pretty nearly 100% quartz. It's a very, very pure quartz sand. Right now it's been metamorphosed. It's a quartzite. We'll see more evidence of that up a little bit farther. But if you turn this over, it turns out you can't tell up from down with these ripples. It looks the same no matter whether it's upside down or right side up. So these will give you the direction of the current, but they don't give you which way is up or down. Now, it's quite possible that there may be places along here where you would find wave ripples also, which would give you the up and down. But these ripple marks won't do it. Okay, let's go up a little bit farther then, over to those ledges over there. Matter of fact, you can probably see better right here. You see the horizontal layers there? That actually is bedding. Those are very, very, very thick beds of sandstone. Well, I call it sandstone. It's actually quartzite now. It's a metamorphic rock. We'll get to see some of the metamorphic effects when we look it up close. But if you have a small piece of that, you can't even tell that it's bedded because the beds are too thick. That's why you can see it better from here than you can if your nose is right up against the outcrop. But let's go put our noses up against the outcrop and see what we can see there. Okay, this is the bedding that you see here. These are bedding planes, very, very thick bedding planes, but there are very obscure vertical cracks in this rock in places. It does tend to split a little bit in this direction. These vertical cracks that you see are a result of that. Now, most of the time when you see that in a metamorphic rock, it's because you've developed sheet silicates. And the sheet silicates, of course, have a good cleavage, and so the rock itself has a really good cleavage. That's not the case here. This rock doesn't have any sheet silicates in it at all. It's almost pure quartz. But if you put the quartz under a directed pressure, much more pressure in one direction than another, it turns out that quartz under pressure is slightly more soluble. It will dissolve a little bit more easily. And if you put a directed pressure on it, you will develop cracks where it dissolves from the two sides of the crack. And so the crack gets a little bit bigger and the rock is pushed together on either side. This is called a pressure cleavage and does not need the sheet silicates to do it. Now the quartz grains are intergrown here as well. When this was just an unmetamorphosed sandstone, it would break around the grains. Now it just breaks right through the grains because the grains are all intergrown with each other. So that's what distinguishes it as a quartzite, a metamorphic quartzite from a sedimentary sandstone. Now, let's go up to the very top. We can go up the steps around the corner there, and we get a good look at the Frederick Valley below.
Yo vi algo con respecto a lo que tú me dijiste en YouTube, no me recuerdo dónde fue que lo vi. Sí, fue que I pulled up the documentary. Pero lo de los nazis que me estabas hablando mucho. Pero vi las estructuras, vi algo, me recuerdo en algún momento.
Ah, la verdad que me vuelve la cabeza no sé,
No, it's not. Or picnic stuff.
Been here before?
Okay.
It's a nice view.
It is, that's the one reason why we do come up to this point, because you get that view, and it's a geological view. I'll have a little bit to say about the geology. Now that it is set up recording?
Yes.
Good enough. The summit
one
of
thing.
Sugarloaf Mountain is up there, and that's the highest point.
You got to stay away from the edge here. You want to feel right there. That's good. Yeah.
It's pointed in the.
Well, it's just at the edge. It's going to be blurry. It's gonna
Okay.
be,
Anyway, this is the highest point in the Maryland Piedmont, and it's a pure quartzite, and those 2 points are related. Why is this the highest point in the Maryland Piedmont? And why are those facts related? Okay, you do have the information in your background that I've lectured on to answer that question, but I'll give it to you anyway. What's the hardness of quartz on the Mohs scale? Remember that? It's 7. It's the hardest of the common minerals. Also, quartz is almost indestructible, not completely, but it's not attacked by acid, and weathering does not affect it much at all. So this whole area has been exposed to wind and acid rain and carbon dioxide, all the weathering factors, for many millions of years. And over that period of time, it has weathered and worn down. But this has weathered and worn down less than most because of the nature of the rock. It's an upfold like this. It's an anticline, and the lower rocks, that is the older rocks, are exposed here in the middle of the anticline, on the crest of the anticline. If you saw the bedding back down there, you saw that the bedding was horizontal. It looked more or less horizontal. When we saw the outcrops down along the creek bed, we didn't get to look at the bedding. It was over on the other side of the creek and was hard to get to. But if you would have seen the bedding there, you would have seen that it's tilted in this direction. It's tilted down to my right. And if we go farther in this direction, it'll be tilted down to the left. And so that's the shape of this particular fold. Actually, it's turned over if you keep following it around. Now, this rock, here, more nice ripple marks right here, by the way. The far ridge over there is the eastern edge of the Blue Ridge geological province. And the highest ridge there is also a nice pure quartz sandstone, slightly metamorphosed, that looks very much like this. But in between, there are several different faults where the rocks have been pushed up and over. Now, is this rock here the same originally as that rock over there? Just two different places where it's exposed? The guess is that that's probably the case. But again, that's an educated guess. because of the faults in between, the thrust faults in between, these rocks are now much closer than they used to be because it's been pushed up and over. And my fist here is farther away. As it's been pushed up and over, it's now a lot closer. So this rock may have been moved 10 miles closer to those rocks over there. And there are actually several different possible layers of quartz sandstone over there that could match this one. Now, the sandstone over there doesn't have any fossils in it either. So, and you can't get a radiometric date on it. But it is associated with other rocks that do have fossils, and we can date it by seeing that it's above some of the fossil-bearing rocks and below others, and we can sandwich it between those dates and get a pretty good idea of how old that quartz sandstone is. This quartz sandstone, if we make the assumption that it's the same as that sandstone over there, we can then make a guess as to the date, like it's the same date as that. If it isn't, well, then we're wrong.
You don't know, yeah.
Yeah. Now, there's a story from, I went to school in the Boston area, and when I went to school there, the Boston Basin contains some low-grade metamorphic rocks. Almost some of it's just sedimentary rock, but there are no fossils in it. Some of it is sandstone, some of it is shale. If you go just to the south, within a few miles, there are very, very similar rocks that extend down into Rhode Island. Those do have fossils in them. And the rocks look, as I say, very, very similar. And when I went to school there, they were thought to be the same age. And they dated the rocks in the Boston Basin by the fossils in Rhode Island. Well, that isn't ideal, but it's the best you can do. A few years later, just about the time after I went to school there, they did get some radiometric dates on the rock in the Boston Basin. And it's about 500 million years older than the rocks in Rhode Island. The fact that the rocks look very similar turns out to be coincidence. It is not a firm way of getting dates. So these rocks here could be very different from those rocks over there. And when we look at the rocks in the Boston Basin, that is a cautionary note on putting too much faith in our assumption that these rocks are the same as the rocks over there, because they look the same. They could be very different. Now, down there, as I say, is the Frederick Valley. And from what I've said about this being the highest point in the Piedmont, because it's a nice pure quartz rock, which is very hard and very insoluble, you would suspect that that rock is a lot softer. Actually, there are two different rocks down there, and we're going to get to see both of them on our next couple of stops. Much of the valley is limestone. And that limestone actually does have fossils in it, so we can put a good date on the limestone. But there's a fault in between. And that fault means that these rocks were not originally associated with those rocks. So we can't use those fossils to put a date on here. But the fact that it is limestone explains why it's a valley. It's a lot softer, it's a lot more soluble. Also, if you go a little bit further south down the valley here, it is a rift valley as well. And we're going to get to see those rocks too when we visit the Rocky Point Creamery for our morning ice cream. Assuming it's open, there is no guarantee on that. Last time I was there, the pandemic had left them shut. Anyway, that too is much softer rock. It's a sedimentary rock. It hasn't been glued together and made hard by metamorphism. So between those two softer rocks, that's why it's a valley. Now, you go over to the ridge on the other side, and as I say, that's a very similar rock to this one, which is why it's standing up as a high ridge. As a matter of fact, you can follow that high ridge for hundreds of miles. You can follow it basically all the way to Vermont in one direction and all the way down into Georgia on the other side. So, you know, it's a major geological feature. The rocks in here, and if you go to the other side of the Blue Ridge, again, then you're in the Hagerstown Valley, which is the Great Appalachian Valley, can be followed all the way from the Canadian border to Alabama, because it's a limestone valley. Now, are the rocks, is the limestone here the same as the limestone on the other side? Probably, again, because there is some faulting in between. It's difficult to say that they're exactly the same, but in this particular case we do have fossil evidence to go on, and we can say that we can match the limestones here with some of the limestones on the other side in terms of age because of the fossil content. Okay, any questions?
Not so far.
Okay, I will emphasize again though that the geology that we're running across here, all the way from Silver Spring to here and off to the west, there are bands of geology, the geologic provinces, and we can follow these geologic provinces all the way from the Canadian border down into Alabama. So the geology that you're learning about here can be applied all the way up and down the eastern part of the United States, because the rocks are very similar, the metamorphic belts are very similar. Everything we learn here is applicable elsewhere in the mountain range. Okay, let's go on to our next stop. By now you have nice ripple marks.
Yeah.
By now you must have this down cold.
Well, no, because you say something different every time.
Oh, I do.
Yes, you do.
I do.
No, if you said everything the same, it'd be dull.
Besides, we'd never get to our next stops.
Right.
Oh,